Friends, in this lecture we shall discuss about modeling of excitation systems. While talking about the modeling, we will study non-reciprocal per unit system. Then we will talk about the modeling of excitation system components, because any excitation system has several components. Therefore, first we will discuss about modeling of the components of the excitation system one by one. The components which we will be model, we will start with the separately excited DC exciter, self excited DC exciter, AC exciters and rectifiers. As you know that in AC excitation system, the output of the AC exciter is rectified and supplied to the field winding of synchronous generator, and therefore, there is necessary to model the 3 phase rectifiers which are commonly used. The other components which require to be model are the amplifiers, excitation system stabilizing circuit, wind up and non wind up limits. As we will see that there exist certain limits, that the output of say AVR cannot exceed a certain limit like this. Therefore, we will have certain limits which are imposed, and there are 2 different categories of limits, wind up and non wind up limits. Then to implement the under excitation limit and the over excitation limit, we will have gating functions and terminal voltage transducer. Over the years, a variety of excitation system models have been developed. We will confine our discussion to a few typical excitation system models which have been documented by IEEE in the standards published by IEEE. We will discuss the excitation models: type DC1A exciter model, type AC1A exciter model, type ST1A exciter model, type ST2A exciter model. They are the 4 models which we will discuss. However, a number of models are available in the IEEE standards. Over the years, the IEEE has developed the excitation system models for power system stability studies. The 4 important references which cover the excitation system models are: the first report, that is first IEEE committee report. This was published in the year 1968 in the IEEE transaction on power apparatus and systems. Then subsequently the models were upgraded, taking care of the new developments which have taken place. Then the next IEEE committee report was published in the year 1981, and when you look into this IEEE committee report, you will see that they have 3 different models for DC excitation systems, 4 different models for AC excitation systems, and 3 different models for static excitation systems. In all, they have discussed 10 different models excitation systems. Now, these different models were needed to cope up with the variety of excitation systems manufactured by different manufacturers and existing in the power system today. Recently, in 1996, another a committee report came in, where they have discussed specifically the digital based excitation systems, because today the excitation systems have microprocessor based controls, and with this digital controls, right, there was a necessity to model the excitation systems and give standard excitation system models. Then one very comprehensive standard, which is IEEE standard 421.5, published in 1992, it discusses in detail the different models which have been developed. The material which we will be presenting here is drawn from these 4 references. Now, here when we talk about the excitation system models, we have to develop the per unit system for excitation systems. We have developed earlier the per unit system for synchronous generator models, and while developing the synchronous generator model, in order to simplify the synchronous generator equations, we had made certain assumptions, and the model developed is normally known as the reciprocal model, right. Now, if we use this reciprocal model, there are some problems, particularly if you use this reciprocal model, then the per unit values of the exciter output voltage becomes very low. The typical values which is mentioned is that it may be as low as 0.001 per unit if you use the same per unit system, and therefore, another per unit system is proposed for modeling the excitation systems, and that is called as non reciprocal per unit system. In this non reciprocal per unit system, the definition goes like this: 1 per unit exciter output voltage is required to produce rated synchronous machine armature terminal voltage on air gap line. As the definition goes, that 1 per unit exciter output voltage is required to produce the rated terminal voltage of the synchronous machine on the air gap line, not on that saturation curve, but on the air gap line. Now, here we define the 1 per unit exciter output current is the corresponding current which flows in the field winding of the synchronous generator. That is, when you apply certain voltage at the terminal of the synchronous generator, which produces the rated voltage at the terminal of the synchronous generator, right. Then at that time, whatsoever is the current which flows in the field winding, we call that current as 1 per unit. I just take an example. Suppose you have a synchronous generator whose terminal voltage is say 11 kV. Okay. Now, to produce the 11 kV voltage on the air gap line, if you require say 600 volts to be applied to the synchronous generator field winding, right, then this 600 volts will be considered as 1 per unit voltage of the excitation system. Similarly, suppose at that 600 volts applied, the field current comes out to be say 200 amperes, right. Then this 200 ampere will be considered as 1 per unit field current or 1 per unit excitation system current. Okay. Now, with this definition, now there is a necessity to establish the relationship between the reciprocal per unit system with the non reciprocal per unit system. We know that the excitation system is interfaced with the synchronous generator both at the field winding as well as at the synchronous machine terminals. That is, for controlling the output of the excitation system, the input control signals are derived from the terminals of the synchronous generator. That is, you change the terminal voltage, you use actually the load compensator and obtain a voltage Vc. Okay? This is obtained from the terminal of the synchronous generator. Similarly, you may change the speed of the synchronous generator, okay? Or you change the power output of the synchronous generator, all these things, right? Real power, reactive power, all these quantities are fed to the AVR of the excitation system, right? Therefore, so far the input to the excitation system is concerned is obtained from the terminal of synchronous generator, while the output of the excitation system is fed to the field winding of the synchronous generator. Therefore, excitation system is interfaced at with the field winding of the synchronous generator and the terminal of the synchronous generator, right? And therefore, we have to have the arrangement so that these two different forms of per unit systems are properly interfaced. Now, in order to achieve this interfacing, we first look at the basic open circuit equations. That is, when the synchronous generator is open circuited, right, we have the equations that ED is equal to 0 and EQ equal to psi d, which is equal to LAD into IFD. Now, these equations, these two equations are the basic stator winding equations in terms of dq axis components. Okay. Now, we know also that under open circuit condition, this voltage or this current axis component is also equal to the terminal voltage of the synchronous generator. This was already established. Okay. Therefore, now if I plot a characteristic relating EQ or ET as a function of IFD, that is the field current, right, then the characteristic will look like this. Is open circuit characteristic of the synchronous generator. On this axis we have marked the field current in per unit IFD. Now, this IFD, when I use this symbol, this is actually the symbol used in the reciprocal system of per units or per unit reciprocal system. And we represent the per unit terminal voltage on the y axis. Now, this is the open circuit characteristic. If you draw a tangent to the characteristic passing through origin, okay, that is the initial portion, then this is your air gap line, right. The slope of this air gap line, is the mutual inductance unsaturated, LADU, that is the mutual inductance unsaturated, that is the slope of this characteristic, right. Therefore, now to produce on this axis I have put this current in per unit of IFD, that is reciprocal system, and for producing one per unit voltage here, the current required will be there is IFD required will be equal to, that is to produce ET equal to 1, that is same as EQ, right. Therefore, IFD required will be 1 upon LAD, and since we are considering here the air gap line, we are considering the unsaturated value of mutual inductance, and therefore, the current required to produce one per unit terminal voltage in reciprocal system of units, right, it is 1 upon LADU. Now, this current will be denoted as 1 per unit in the non-reciprocal system of units. That is same quantity, okay, will be said as 1 per unit. Okay. Therefore, using this information we can establish the relationship between the non-reciprocal per unit system and reciprocal per unit system, because we have seen actually that the IFD required to produce 1 per unit terminal voltage is 1 upon LADE U, right, and since this should be equal to 1 per unit in the non-reciprocal system, and therefore, the relationship which is established between the non-reciprocal system of unit, we call the current in non-reciprocal will denote by IFD capital. Okay. In the reciprocal system we have been using this symbol IFD. Therefore, the IFD will be equal to LADU IFD. This you can check yourself, that the relationship between the reciprocal per unit system of field current and non-reciprocal per unit system of the field current, they are related by this quantity LADU. Okay. That is, similarly, when we talk about the field voltage, okay, the EFD, the field voltage EFD is equal to RAFD IFD, okay, and I replace this IFD by 1 upon LADU. So, that the EFD is applied, it becomes RFD upon LADU in per unit, right, and this is denoted as 1 per unit. So far actually the non-reciprocal per unit system is concerned, and hence the relationships which we establish are like this, that in non-reciprocal per unit system the field voltage EFD is equal to LADU divided by RFD EFD in the reciprocal system of units. Therefore, these two equations, that is equation 16.5 and 16.6 relate the field current and field voltage in reciprocal system of per unit reciprocal system of units to non-reciprocal per unit systems. Okay. Now, here I have shown in the form of a block diagram exciter model non-reciprocal per unit system, right. We have exciter model. Now, the quantities will be EFD and IFD. Okay. Synchronous machine model reciprocal per unit system. The quantities at the terminals of the field winding are EFD and IFD. Okay. The relationship between these two quantities, that is EFD is equal to RFD upon LADU EFD and IFD is equal to IFD upon LADU, right. Therefore, whenever we develop the complete model of the system, right, considering the synchronous generator and the excitation system, right, the excitation system first will be modeled considering the non-reciprocal per unit system, and then it will be interfaced with the synchronous machine reciprocal per unit system using these relations, right. Now we will devote our time for discussing the models of 3 basic components of the excitation system, that is separately excited DC exciter, self excited DC exciter, AC exciters and rectifiers. Now, as I have told you earlier that although the DC excitation systems, right, have been superseded by AC excitation systems or static excitation systems, but still in the power systems existing today, there are number of DC excitation systems operating, number one. Second point is that when we develop the basic model for separately excited DC exciter, the model for AC exciters is also similar to that with some modifications. Okay. Therefore, let us start with developing the model for separately excited DC exciter. Okay. Now, in order to develop the model for the separately excited DC exciter, you look at the DC exciter. This is the armature of the DC exciter. Okay. It is a DC exciter it's a field winding. Okay. This is the field winding. We represent the field winding by a resistance Ref and inductance Lef. That is, this field winding of the DC exciter, right, has resistance and inductance. Right. Now, the field winding is generally very highly inductive, right, and therefore, the inductance plays very significant role in the modeling of excitation system. Okay. Therefore, we will start like this. Let us say that the voltage applied to the terminal of the field winding is EEF and the current flowing is IEF. Okay. Now, here the output voltage of the exciter, right, we call this as EX, this is denoted by the symbol EX. Okay. Now, this EX is related to IEX, okay, and the relationship is a non-linear relationship. We all know actually that if you plot the open circuit characteristic of a DC generator or separately excited DC generator, it comes out to be a non-linear characteristic. Saturation exists in the system. Further, when this DC exciter is loaded, right, due to armature reaction, the voltage at the excited terminals will further drop, right. Therefore, while modeling the DC exciter, we may have to account for two things. One is the loading effect, another is the saturation effect. And in fact, while modeling the DC exciter, we combine both the effects. Okay. Now, the basic equation for the field circuit is written as the EFD. It should be slightly mistake there, EFE. We will denote the symbol by EF. The mistake here, you make it EEF. EEF is equal to REF into IEF plus d psi by dt, where psi is the flux linkage which can be written as LEF into IEF. This is the basic circuit equation of the field winding of DC exciter. The output voltage of the exciter is proportional to field flux linkage psi, and Kx is a proportionality constant. That is, output voltage at the terminal of the synchronous generator, output of the exciter, DC exciter, not synchronous, is directly related to the flux linkage of the field winding and is directly proportional. Okay. Now, this constant Kx depends upon the speed of the exciter. It also depends upon the design of the exciter and other parameters. Now, here this is the most important point to understand about modeling of DC exciter or separately excited DC exciter. If we plot the open circuit characteristic relating the Ex to IEF, right, then this open circuit characteristic is shown here. okay, and when we draw the tangent to this, we get air gap line, right, and the slope of this air gap line, if you find out the slope of this air gap line, right, then it is, because this is a steady state characteristic, this is a steady state characteristic. What will be the slope of this? Resistance of the field winding, okay. And since we are considering the air gap line, we will consider this resistance as R g, shown here. Now, if suppose for a certain output E x o, right, if I try to find out what will be the field current required under the open circuit condition, then the field current will be equal to the field current required corresponding to the air gap line plus some additional current to account for the saturation. Now, in order to account for the loading effect, right, what we do is that we plot another saturation characteristic, and that characteristic is shown here. This saturation characteristic is the constant resistance load saturation curve. We have to understand very carefully what we mean by the constant resistance load saturation curve. Now, this can be explained like this. You have your DC generator armature, across this you put a resistance, okay, and this is the field winding. Call this current as IEF, okay, and run this machine as rated speed, and now if you plot the characteristic relating the terminal voltage E x with respect to IEF, this characteristic will take care of two aspects, saturation as well as the armature reaction effect, and this characteristic is called constant resistance load saturation curve. Okay. Now, for a given value of E x, the field current which is required will be now written as the field current corresponding to the air gap line plus this additional term delta IEF. This delta IEF, this is the additional quantity, right. This takes care of saturation as well as the loading effect. And therefore, now we can say that for any operating condition, the IEF will be equal to E x divided by R g plus delta IEF, delta IE. This additional current which is required to account for the saturation and the loading effect, right, is function of the voltage E x which is produced and a non-linear function of E x. That is, if I try to quantify what is the value of IEF required, then we can easily see here actually in this graph that this IEF is different for different values of E x, right. Therefore, we can say that the IEF required is equal to the voltage E x into a nonlinear function S E E x, and this S E E x is called the saturation function, which is dependent on the voltage E x. In fact, this has to be obtained graphically. This value, whenever you want to, you can say, develop the model for a given DC exciter, this has to be obtained experimentally. Now, what we do is, we have developed basic equation starting from the field circuit equation, that is EEF is equal to REF into IEF plus d psi by dt, where psi is the flux linkage. Now, what we do is that in this expression, in this first basic expression, in this equation, that is EEF equal to REF IEF plus d psi by dt, you substitute the value of IEF, substitute the value of psi, okay, and we will get, after making this substitution, an equation of this form, that is EEF is equal to REF upon RG EX plus REF into SE EX into EX plus 1 by kx d EX by dt. That is, when we have obtained this equation, we have made use of the subsequent relations which were derived earlier. Now, in this equation, we can see here that the field current is eliminated. There is no field current term, does not appear directly, okay, and there is no flux linkages also. Everything is expressed in terms of the saturation function, the field resistance of the field winding, and this constant kx. Okay. Now, this equation is converted into per unit system of equations. Therefore, what we need is the base voltage for this, that is IEF, we require base voltage, and the base voltage is chosen like this, that is EX base is same as the EFD base, that is the field voltage which you apply, right. That base value is the base for EX, and IEF base is same as EFD base divided by RG, that is the base value of the field current, as we already seen that this voltage divided by the air gap by the slope of the air gap line, that is resistance RG, and the resistance base is equal to RG itself. Okay. Now, when you convert this equation into per unit system of equations, that is, you divide that, you divide this equation by EFD base throughout, and then you can write down the equation in the form EEF bar. Bar stands for per unit, and this conversion is right now, it is actually the non-reciprocal per unit system. Okay. Now, when writing this equation, okay, some new terms are introduced here which are defined as follows, that is SE bar EX bar is defined here as SE bar EX bar is defined as delta IEF bar divided by EX bar. They are very straightforward definitions which you can derive, and I will suggest you to derive these things yourself. Okay. Now, here again I am showing the constant resistance load saturation curve of the DC exciter. Now, on this axis, now instead of putting the field current in reciprocal per unit system, I am put this field current in non reciprocal per unit system, right, PUIEF. and this is per unit E x. Okay. Therefore, now you can see in this equation that for any value of E x, right, the field current required will be so much. Right. Now, I call this quantity as A, and the field current required corresponding to the air gap line, that is the, if we neglect the saturation and loading effect, field current required is denoted by B. Okay. Then this saturation function which we have defined can be written as simply A minus B divided by B. Okay. And by the basic definition of K x, the K x can be expressed again in terms of the per unit output voltage of the exciter and the per unit field current. Okay. Now, here we have a term, that is K x is equal to R g divided by L E f E x bar I E f bar. Okay. Therefore, what we do is that we define another term which we call as L f u is equal to L E f I E f o E x o bar. That is, for a given operating condition, right, you can denote this term as L f u, that is this L E f I E f divided by E x. You can call this term as L f u. Now, if you denote this term by L f u, then our equation will reduce in a standard form, that is E E f bar equal to K E E x bar S E E x bar E x plus T E d E x bar upon d t. That is, you can see this equation here, that you have all per unit voltages, saturation function, which we, as I have told you, that can be computed from the constant load resistance saturation curve. Okay. Now, once we have come to this level, we can write this expression in the form of a transfer function model, because when I said that I want to develop the excitation system model, then we can express this model. This is now the excitation system model of a DC exciter. Okay. Now, this can be put in a compact form in a transfer function model. That is, what you do is that you take the Laplace transform of all these quantities, right, and when you express this in the transfer function model form, it looks like this. We have seen, you just look at this equation. If you look at this equation, what is to be done is, at one summing point you have the term K E E x. To this K E E x you add this term, they are the two algebraic terms. Okay. You add these two terms, subtract from I E f, that is E E f, okay, and when this whole quantity is integrated, you will get E x, right. Therefore, this model comes something like this in the form, here is E x. Therefore, you this is the gain K E. Therefore, output from this block will be K E into E x. Output from this block will be a saturation quantity, that is V x, which is E x into S E E x. Okay. These two are added and subtracted from E E f. Now, whatsoever comes is multiplied by this transfer function, you get the E x. Therefore, the transfer function model of a separately excited DC exciter is given here. These quantities, all these quantities are expressed K E, T E, K E and the saturation function, right. They can be easily computed from the relations which have been derived. For example, Ke is equal to Ref by Rg, Te is equal to Lfu by Rg, and Se Ex bar is equal to Se bar Ex bar Ref by Rg, right. Therefore, these quantities are all known to us and they are obtained from the parameters of the DC exciter and the constant resistance saturation curve. Now, this block diagram which I have just shown can be further simplified and put in the form of a first order transfer function, because here we have seen actually it is a first order transfer function. Therefore, the whole thing can be simplified and you can make this model as a small perturbation model showing a small change in the field voltage applied to the exciter and small change in the output voltage delta Ex, right, can be written in the form of K upon 1 plus S times T, because we are whenever we represent any system, right, we always try to develop a model with input output quantities, okay, and the transfer function models are always linear models. Non-linear models actually we do not have anything like transfer functions. Okay. Now, the model which I have developed here will be applicable for one operating condition. For once you take one particular operating condition and take small perturbations around that, then a small perturbation model is put in the form of a transfer function model, right. These quantities K and St are given by these equations. Here K is equal to 1 upon Bex Se Ef do plus Ke. I will just explain this term Bx separately, and T is expressed as Te divided by Bx Se Ef do plus Ke, where the Se Ex, so this saturation curve, this is the nonlinear saturation function. This is modeled by this exponential function, a constant Aex e to the power Bx Ef do. At any operating condition, right, we can find out the value of Se Exo either graphically, or if you have modeled this saturation function by this exponential function, where these terms will be known to you, right, then that is why actually the constant K and this T are expressed in terms of the parameters of saturation function, and all other parameters like K is there, T is there, right. Now, next point is that we will develop the model for a self excited DC exciter. Okay. Now, the self excited DC exciter will look like this. You have synchronous, the armature of the DC exciter. This is the field winding of the DC exciter. We will have some regulating rheostat in series with this field winding, right, and the output of the AVR, will be connected in series with the field circuit and put across the armature. That is, in case suppose it is not a regulated one, right, then we will connect this field winding directly across the armature. But here what we do is that in series with the field winding we connect the output of regulator, right. So, that here we can write the EEF equal to VR plus EX, VR plus EX, that is in case it was a separately excited exciter, EF will be same as VR, but now EF is going to VR plus EX. Now, with this change, this is the only change, with this change one can develop the complete model of the self excited DC exciter. That in the equations which we had derived earlier, that is 16.22 is substituted, the substituting equation 16.22 in equation 16.13, right. That is, wherever we had this EEF, we are putting VR plus EX, other things are same, but that is the only change actually in the circuit. Okay. When this model is simplified, you will find actually that the same model which we developed for separately excited DC exciter is applicable, except the definition of Ke now becomes Ref divided by Rg minus 1. This is the only difference, other things are exactly same. That is this model. See this model, this was the model developed for separately excited DC exciter, right. Therefore, the Ke which was defined is now modified for a self excited DC exciter, and the value of Ke comes out to be Ref by Rg minus 1, and other definitions are same. Okay. Now, with these definitions, okay, we have completed the model for DC excitation system, that is self excited as well as series exciter. And what we see here is that it comes out to be a first order model. The model is a first order model. Okay. Now, when we go for AC excitation system, in AC excitation system we have the main source of field power is AC generator, an alternator. The output of this alternator is rectified with the help of 3-phase full wave bridge rectifier. Now, this 3-phase full wave bridge rectifier may be controlled or uncontrolled. Okay. Now, in order to develop this model, we account for the demagnetizing effect or the armature reaction effect separately. In the case of DC exciter, we have accounted for the armature reaction and the saturation together, while in the AC exciter the practice is to separately account for armature reaction, and the characteristic of the AC exciter, which is plotted under no load condition, there is open circuit characteristic plotted under no load condition, the open circuit characteristic, right, because open circuit characteristic always under no load condition, right. The open circuit characteristic is used here, and the saturation is defined making use of the open circuit characteristic. That is, you plot the open circuit characteristic, on this axis you are putting the per unit exciter field current, and it is the per unit VE. Now, here this VE is not the voltage which is applied to the field winding of the synchronous generator, but VE is the output of the exciter. Okay. And the saturation function which is required here in this model, the saturation function is obtained from the open circuit characteristic. Okay. Now, to account for the armature reaction effect, we have one more block here, where the actual field current IEFD is multiplied with the multiplying factor Kd, which is called demagnetizing factor, and that is Kd into IFD is added at this point. Therefore, if you see the complete model, the difference between the DC exciter and AC exciter is, one is this term, that is we are putting additional term to account for the demagnetizing effect. Second is that this saturation function is obtained from OCC, right. And third thing is that the output here is the terminal voltage of the exciter, not the voltage applied to the field winding, because this voltage which is the output of the exciter is rectified and fed to the field winding. Therefore, there is a rectifier in between. This is all main difference between the DC exciter and AC exciter. Now, as I have told you that this is saturation is obtained by this formula AB minus B. The output of the rectifier is denoted by EFD, that is a function FEX, a multiplying factor FEX into VE. This is very important. This FEX is a very complex function, and as we will see actually that we have to model the rectifier characteristic. The three phase rectifiers, when they see the system, there will be the input impedance is purely inductive in nature. Input impedance is purely reactive in nature, and this impedance has the effect of delaying the commutation. And when there is some delay in the commutation means the change of current from one valve to the another valve, right, and this affects the output voltage. Now, for modeling the three phase rectifiers, we always define three different modes: mode 1, mode 2, mode 3. These three modes are depending upon what is the load current, how much current it is supplying, right. It is very nonlinear characteristic. Therefore, to obtain the characteristic of the rectifier, or this is a rectifier regulation model, what is done is the output of this AC exciter is multiplied with a multiplying factor which is obtained through this loop. That is, you have VE multiply by some term, you get EFD. This multiplying factor, as I have just now told you, is FEX. FEX is the multiplying factor. Now, this FEX is obtained from IFD, the field current flowing in the field winding of the synchronous generator, and output voltage. That is, you obtain a nonlinear, obtain a function IN equal to Kc IFD by VE. That is, using this terminal voltage which is available, what is the field current which is supplying, we obtain a current IN, and this FEX function is a nonlinear function of IN. That is, FEX is equal to a function of IN. Now, here in mode 1, FIN is equal to 1.0 minus 0.577 IN, where IN is less than 0.433. This is in the mode 1. When you are operating in mode 2, FIN is equal to square root of 0.75 minus IN square, where IN is greater than 0.433 and less than 0.75. And we are operating in mode 3, this function FIN is equal to 1.732 into 1 minus IN, where IN is greater than 0.75 and less than 1. That is, this nonlinear function, okay, is different for different modes, and they can be computed using these expressions, while IN is computed knowing this IFD and VE, and this factor Kc, which is the commutation reactance. Kc is this Kc stands for a constant which depends upon commutation reactance. Right. Now, with this I conclude my presentation saying actually that we have developed the non-reciprocal per unit system for excitation system, and we have developed the models of the DC exciter, that is self excited and separately excited, and AC exciter. Right. We will continue the discussion on modeling in our next lecture. Thank you.